This is a very short chapter on the kinematics of equatorial waves. Well, actually, we don't say anything very specific about the equator, but in general, we need to remember that the atmosphere has these kind of complex background states. It's not a uniform flow, it's not at rest, it's not steady, zonally or latitudinally uniform, and so on and so forth. You remember this diagram or this figure of the seasonal zonal mean meridional section of the winds for June, July, August, September, October, November, December, January, February, and March, April, May. We looked at the low latitude easterlies and the vertical shear, jet streams, etc., and the meridional winds being strong at the top in the deep tropics and at the surface in opposite directions, corresponding to the ITCZ, its movement, and the Hadley cell, right? So when we think about waves, we always think about moving forms, and obviously they don't carry much mass, but they can carry energy. This is an example of Raspy Waves ray paths in the atmosphere being generated here in the Pacific during an El Nino spring, and then they are going eastward to the Indian Ocean region, and another path goes southeastward and then across into the southern Indian Ocean. So we will see, or you probably already heard, that Raspy waves in the atmosphere tend to propagate west, but you can have background states doing things to the waves that change their wave number, their modes, their group velocities, and lead to aggregation of energy and so on. So we'll look at some of those things. Kinematics obviously means that we just look at velocity, acceleration, interactions without worrying about the forcing and so on. So ray path, which I showed here, basically is something like this, where you have, let's say you threw a stone into the pond, or some sort of energy source, acoustic wave, let's say, that is traveling out in circles, and this is the waveform here, and there is the wave front going forward, and that's the ray path. It turns out to be much more complicated in the atmosphere, as we'll see later on, so we'll just get introduced and oriented to certain basic ideas in this chapter, starting with the dispersive and non-dispersive waves and phase and group velocities. So if you have a waveform here that's coming and hitting some, let's say, background state or something, then you can see that this wave is dispersive, so it begins to change its waveform. You'll see that it became broader. It's still got this envelope that changes, whereas this non-dispersive wave doesn't change. It just continues as it is. You can think of this as a atmospheric wave hitting a mountain, or changing from ocean to land, and so on and so forth. I think you have some idea about group and phase velocities. Phase velocity is the speed with which individual form is moving in this particular case, and you can see that they can be the same in a non-dispersive wave. So here phase velocity is the same as group velocity, so the envelope is moving at the same speed as the individual forms or waves. They can also be opposite depending on how the waveform is getting generated and destroyed ahead. So you can see here phase velocity is getting small here and then growing again, getting small and growing again. In this case, the envelope is actually moving backward, as you can see here. This is other examples, phase velocity being greater than the group velocity, and so on and so forth. Okay, the other concept we need is something called Stokes Drift. So as we said, waves don't actually move much mass, but let's say you are sitting at a pier and looking at a wave going through water. This is a combination of transverse and longitudinal waves. So the particles make this orbit here in a circle. Let's say it's a perfect wave, in which case each particle is making this circle. But let's say there is some junk floating in the water as you are sitting and watching, and the wave is not so perfect, then the particle may not return to the same place. It might begin to move in the direction of the wave by a tiny bit, not as fast as the waveform. So that is called Stokes Drift. It's kind of a rectified motion because of the wave not being so ideal in reality. Okay, so reaffirming those concepts, let's look at phase and group velocities and energy propagation. So when we talk about waves, especially in the ocean, in the atmosphere, in the tropical dynamics, we will see that they are critical for energy transport, energy propagation, and if they are in this non-constant background, varying background, and their modes and group velocities, wave numbers, etc. change, then obviously that means energy dispersion rates can also change. So let's start with this example of throwing something in a pond. Results in kind of a Dirac delta function of perturbation, which then moves out in waves and then eventually dissipates. And if the water was very calm before, then you will get such perfect waves, and we have to then look at the wave characteristics in a quiescent basic state. You know that we're going to add complications soon. So you can see here an example of how such waves can also form in the ocean. We have in the ocean, this is like the West Pacific. You can see New Guinea here, Philippines here, the Asian coast, Japan, and so on. So let's say this is a storm. So in the ocean you have sea, where the storm is generating waves and churning the ocean, and various waves get formed. The longer waves move faster and get out ahead of the storm, and you can see that more clearly here. So this is the storm, and you have waves going out as swell. They become sorted into nice calm swells, which then hit the coasts and then become surf, right? So you have sea, swell, and surf typically in the ocean, but that gives you a good example of how the background state can make a difference. And then you also run into islands, bottom topography, and so on. To do the analysis of the perturbation in the pond, we can write a waveform with amplitude A0 times the wave function cos kx minus omega t, where of course k is the wave number in direction x and omega is the frequency. In this case, if the wave is just a non-dispersive wave, the phase speed will be just omega over k, so frequency divided by the wave number. Obviously, you know how to derive the other quantities that you have thought about, you have seen before in some basics physics class or fluids class and so on. So you can imagine the wave transect, looking at it at time t, t plus delta t, and t plus 2 delta t, and the wave front is translating this way, propagating this way, so it's not changing its form, it's moving at constant speed. So here, amplitude distribution of a simple sinusoidal wave of amplitude A that we wrote before. Wave number is k at time t plus any future time. The speed of the crest is the phase speed. We note here with omega divided by k, and then we will see another figure a little bit later on, which shows a combination of two waves which are nearby, so k plus delta k, and frequency is also nearby, omega plus delta omega, and they are initiated at time t and t plus delta t, and we will see how there the phase speed of the two modes will change. Okay, we'll come back to that as an example of a dispersive wave. So the equation for that, but the two waves in that case can be written as AXT equals A0 plus A0 times cosine k minus delta k x minus delta omega t plus, so the two waves are interacting with each other obviously as they are moving together, cosine k plus delta x x minus omega plus delta omega t. Okay, so using this rule, cosine a plus b plus minus b is cosine a cosine b, minus plus, so here plus minus, you have minus plus, sine a sine b. So you can use that to write these as cosine kx minus omega t plus minus delta kx minus delta omega t equal to cosine of kx minus omega t times cosine delta kx minus delta omega t minus plus sine of kx minus omega t sine of delta kx minus delta omega t. Nothing fancy, we're just taking this waveform and we are using this equivalence to rewrite the phase functions. So that way we can rewrite this equation then as a of xt equal to 2a0 cosine delta kx minus delta omega t times cosine of kx minus omega t. So this is now a modulated wave. You had two waves starting off, and by interacting with each other, the amplitude is getting modulated and the wave number frequency form is getting modulated as well. So in this case, phase velocity of the group or the group velocity. Okay, so in the first diagram where we saw the animation, we were looking at phase speed of individual waveform, and the entire group was moving, and they could be moving at different speeds or even different directions. So in that case, the phase velocity of the group of waves is called the group velocity. So it's given by delta omega or delta k, which we'll see in the figure in a minute. And in that case, for a general form, we can write the group velocity as d omega dk. You have seen this before, I'm sure. So here is the second part of that figure. Instead of just having one uniform non-dispersive wave, now we have two waves that started out, and then their amplitude is getting modulated, and the entire waveform is a group moving forward as a group. So you have two things. You have the phase velocity here and the group velocity here. So this is the speed with which the group is moving, and this is the speed with which individual waves in the group are moving. So now you have two things, the phase speed and the group velocity. And obviously it turns out that group velocity is critical for energy transport, energy propagation. Okay, with those simple concepts, let me stop the first podcast and then come back to a second one soon. All these are simple concepts you have seen before, so I'm not going very slow in this case. I'm just kind of run through them.